there is a possibility that you're thinking, I know how to balance reactions, this is going to be easy. To which I would say, how long have you been taking chemistry? It's going to be a little bit bigger than what you're used to, but that's okay. Now, don't really do this, because balancing by inspection, we're going to find a flaw in this pretty quick. But if I gave you a reaction and asked you to balance it, this one would balance in terms of the numbers of atoms like this, and it would actually work out pretty well. If I asked you to further dig into that and come up with what's been oxidized and what's been reduced, you would hopefully figure out that sulfur has gone from a -2 to a +4 rather. It's been oxidized, and oxygen has gone from a neutral 0 to a -2, and it's been reduced, and we know how to do all of that. If I were to say dig deeper and tell me that it's actually been balanced, because if electrons are going to be lost, they need to go somewhere. If electrons are going to be gained, they need to come from somewhere. So my total oxidation, total reduction have to match up. Sulfur then, 6 electrons per atom, but if the balancing number comes into it at 2, well, that's 12 electrons that have been moved. And oxygen, total of 6 atoms, and each one is 2 electrons on the move, also 12 electrons. So that works. Here's the problem. It's not going to work much longer. If I gave you a reaction, said this happens in acidic solution, as if that's somehow important, and asked you to do this, you could, you should not, so don't even write this down, you could try the same thing. It would fail, so don't. But if you did try the same thing, you would actually balance it quite quickly by the numbers of atoms. If I asked you to identify what's been oxidized but what's been reduced, you would say that chlorine has gone from a +5 to a -1, and iodine's gone from a 0 to a +5. And true enough, that's what's been oxidized, that's what's been reduced. If you were to dig deeper, my apologies, then you would come up with 2 atoms of chlorine changing 6 electrons. That gives me a total of 12 electrons on the move. Iodine, 2 atoms at 5 electrons, only 10. So I've got mystery electrons. I've got disappearing electrons, or actually electrons that magically appear. Can't have that. So that is not a sufficient way of balancing this reaction, which means all of that stuff that you learned before about how to balance reactions does not necessarily work for redox, and definitely does not work anytime you see the phrase in acidic solution. So what do we do? Well, let's figure out what happened first. The problem is that total electrons lost have to equal total number of electrons gained, and they didn't. The other thing is, and I've already said that, so I'm not going to repeat it. The other thing is, I've already said that, there we go, in acidic solution, I've got water. Water isn't normally a reactant, normally it's a solvent, but what about the acid? The acid has a charge. It's got the hydronium ion, the H plus is in there. And then it can also be available. It could be perhaps available to gain electrons. It's not, I mean, an H plus isn't going to give up electrons, but water could, and we know that water can convert to acids and bases and so on. So we know that those things can be an influence. So we have to take that into account. So I'm going to work through the steps, and to me the way to think about these steps is go from large to small. So I'm going to start with the biggest things I've got, not necessarily the biggest in terms of the overall mass or anything else like that, but from big down to little, and I'll show you what I mean by that. Same reaction. We're going to get this one, we're going to balance it correctly. We're first going to write the oxidation reduction half reactions. It doesn't really matter which one is which, just write out the 2 half reactions. So the chlorine piece and what it ends up with. The iodine piece and what it ends up as. So all of my stuff is now down there. I don't know which one is oxidation, which one is reduction, because I know it was on a slide previous, but I forget. And it doesn't matter. They don't have to be identified at this point. You'll notice I left a gap. I'm going to be filling things in. I'm going to do this that every time I do a new step, I'm going to write out all of the reactions in full. I just think that's a little bit more clear where I'm at right now. Eventually, though, you don't have to do it that way because it takes up a lot of paper. If you leave a big enough gap, you can sort of slot things in. I wouldn't do that for every step, because sometimes we do need to change everything, like double everything or times everything by 3, and that gets pretty cluttered. So every time I rewrite the reaction, I run the risk of writing it wrong, but if I make it too cluttered, I run the risk of reading it wrong. So we're trying to find that balance. going to balance all the big atoms, everything except hydrogen and oxygen. So in this case, the chlorine is already taken care of. There's one on either side. But the iodine, there's two on one side and none on the, one on the other. One, none, two. So I have to balance the iodine on the product side. Okay, big atoms are taken care of. Next smallest one, next way down is oxygen. Oxygen is bigger than hydrogen. So I'm going to balance oxygen. I'm not going to add oxygen. What I'm going to do is I'm going to add water. Now if you're thinking that changes the hydrogen, yes it does. We'll balance that later. So on the first one, I've got 3 oxygens on the reactant side and none on the product side. So I'm going to add 3 waters. Other one I've got kind of something different, so I'm going to add 6 waters to the product side. Sorry, to the reactant side. So now my oxygens are balanced, but my hydrogens are not. Next smallest thing is hydrogen. So now I'm going to balance the hydrogen. I'm going to add H+. Remember, I'm in acidic solution. I've got H+ floating around. Now you might be thinking, I thought it was H3O+. Yeah, but H+ is simpler, and all we're doing here is trying to run a bookkeeping exercise to kind of get our atoms. So we're keeping things as tight as we can. Okay, so balancing the hydrogen, 3 hydrogens on the product side, none on the reactant side, add 6 H+. I've got 12 on the reactant side for the second reaction. That means I need 12 on the product side. Okay, now where I ran into a problem last time was with the electrons. So now the electrons is the last thing I balance, but it's also the most important thing I balance. This is also a thing that's going to cause the most headaches. So I'm going to balance the charge by adding electrons. Now here's the thing, I'm adding electrons. Electrons have a negative charge. I can take a positive charge and I can add electrons to make it more negative. I cannot change a negative charge by adding electrons. So on the chlorine reaction, I've got a -1 plus 6. Total is +5 on that reactant side. On the other side, I've got a -1. So I can bring my +5 down to -1 by adding 6 electrons. In the second reaction, iodine neutral, water neutral, 0 charge on the reactant side. On the product side, I've got 2 -1s and 12 positives. That gives me a total of 10, which means I need to bring that down to 0. I'm going to add 10 electrons. Now remember, total positive charge equals total negative charge, total number of electrons lost equals total number of electrons gained. 6 and 10, they're not the same. I'm going to have to do something to make those numbers the same. So what I'm going to do is the first reaction I'm going to multiply by 5, second reaction I'm going to multiply by 3. Now this is a step that I would recommend you actually rewrite it. So you can have a big enough gap and you can drop in all those things that we did before, but once you start squeezing numbers in and changing that 6 H+ to a 30 H+, strongly recommend you write it down again, because otherwise it's going to get really messy and hard to read. And it's not going to bother me, but it might get you messed up. Okay, those reactions become that. I'm not going to read through them. Then what I'm going to do is I'm going to reduce and combine, because if I look at those reactions, I've got 30 H+ in one on the reactant side, 36 H+ on the product side. Well, most of those are going to knock each other out. So like, for example, 30 electrons, which was the whole point. 30 H+ with 30, leaving a 6 behind. And then most of the waters on the left with all of the waters on the right, and so on. So what that's going to give me is combine those reactions, and I end up with that as my balanced chemical reaction, my balanced redox chemical reaction. Seems like a lot. It is, but this is where we're at. Okay. Steps again, write out the half reactions. Balance all the big atoms, everything other than hydrogen and oxygen. Balance oxygen, it's next big. Balance hydrogen, it's the smallest of the atoms, using H+, and then balance the overall charge using electrons. And again, this last step is the thing that's going to be where most of the mistakes happen, because it's hard to think about adding negative charges. And then make sure that the totals add up and multiply reactions as you need to, and then you're going to combine and reduce, or reduce and combine. And after that, I'm going to leave you with one to try. I don't think I've got a final answer here. Oh, yes, I do have a final answer. There you go. I have a final answer here so you can check, but please do this on your own. But when you are done and you get to check it out, then it should be that, and they combine to be that. But please do this on your own to double check that you're doing the same thing. And then what would we do? Well, all we did was balance redox reactions. So not a lot of stuff going on, but at the same time, a lot going on. And we'll get some more practice in class.